Hi, welcome back to the fourth session of the chapter 2. I'm Ashwin Desai, your physics tutor. Now here in this today's session, we will be seeing the relationship between the electric field and the electric potential. Second, we will be discussing about an equipotential surfaces and their properties, and then later we will be using this relation in getting the electric potential of a conducting solid sphere as well as a non-conducting solid sphere. So this is, students, a topic of this today's session. So let us quickly begin with it. Now students, this time we are interested in getting a relationship between the electric field and the electric potential, right? Let me just consider a positive charge to be placed at some origin O. And here, students, I'll be choosing the two adjacent point. Point A, which is at a distance of some R1 from the source charge, and let point B be at a distance of some R2 from the source charge. Now here, students, this two adjacent point A and B, let me just say that they are very close enough so that the electric field at these 2 points is almost going to be a constant. Okay, and let dr be a distance of separation between these two adjacent points. Now what we're going to do, students, let me just take a test charge. Let me just place it at a point A. And I know that soon there will be an electric repulsive force on this test charge due to my positive source charge, and that will be equal to Q times vector E. Right? Now, if I want to move this test charge from point A to point B, we know that there's still some work done, right? And in doing that work, we have to bring external force here into the picture, right? Now, if you remember from the very first session, students, of this chapter, right, we already defined an electric potential difference, right, which says whenever work is done, right, by an external agent in bringing that unit positive test charge from one point to another point against the electrostatic force, that, students, will be giving you the potential difference, right, between those 2 points. Now this is what the mathematical, mathematically, we can write it, that the potential at B, right, minus potential at the A will be equal to the small work that you're going to do, right, that is dW external over the test charge. Now what is that external work, right? We know that it will be a product of external force into the displacement that you are doing here, right? And here in this case, students, what is that F external? F external, if you just see, is minus of Q times the vector E, right? Because since it's in opposite direction of the electrostatic force, right? And even, students, if you remember, here we also consider a few assumptions, right, where we have taken that we have taken one of the assumptions was the acceleration of this test charge will be a 0. That is, we're going to move this test charge with a very small constant velocity, right? That was the assumptions, and that is why, students, F external will be equal and opposite to the the electrostatic force that is exiting here, and of course the displacement, right? So this is what the equation vector F external dot vector dr divided by Q naught. Now, students, what is this VB and VA, right? Will they be the same? No, not of course, right? If we just see, students, we know that electric potential it is inversely proportional to the distance. That is, as the R increases, the potential decreases. So if I consider some potential at A, that means the potential at B should be slightly higher, right, since it's closer to the from the source charge. So I can write it to be as a V plus dV, right? Now this I can substitute that. What is VB? V plus dV minus VA is nothing but V, right? And on the right hand side we are having this. Now, students, if you just see, right, what is happening, V and V will getting cancelled out from the left hand side, right? On the right hand side, the test as Q naught and Q naught get cancelled out, and what we have available here is dV. It's a small change in potential, right, will be equal to minus vector E dot vector dr, right? Well, now, students, here if you just see, right, I know that the displacement that we are doing here of this test charge is in this direction, right? But as of now, students, I won't be taking that sign. I know that, students, since they are both in the same direction, external force as well as displacement in the same direction, the work done by an external force will be a the positive, right? That is what I can say, right? But students, this dr that you see here is just an increment. Okay, whether it is going to be, it can be a positive, it can be a negative as well, guys, right? And the same equation, when you will be taking it into the integration, okay, over there when you will be substituting the limits, that will be taking care of this the increment, which is a dr, okay, whether you're going to get a positive increment or negative increment. So when you do an integration, the limits that you're going to put up there, that will take care of it. Okay, so as of now, I'll just keep it as it is, right? But students, I'll be considering, like, since the charge q is at origin, right, and the electric field will be, students, along the x-axis. Okay, let me choose this, the vector dr. Okay, here the component of this vector dr to be also along, the same x-axis. Okay, so when I said it is along the x-axis, students, the vector e will be the e I cap. I can write it, right, the component of e along the I cap, right, and as well as, students, vector dr, will be also, I can write it as a dr I cap, right. So I cap dot I cap, students, that will give me a 1, right, and this is what I can write it, dv is equal to minus, e dr. Now I can, write it something like this as well, e is equal to minus dv by dr. Right? Now if you just see, students, what is that dv by dr tells you, right? It's nothing but the rate of change of potential with the distance, and for that we call, as, the potential gradient, right? If I want to know the electric field at a particular point, right, since it's nothing but the negative of the potential gradient at that particular point. Now another thing, students, okay, the sign over here in this equation, you can see the negative sign, basically tells you, the direction of an electric field. So here in this case, the direction of an electric field will be in a direction in which you will see the electric potential is getting decreased. So we know that it's as R increases, right, the potential decreases. In the same direction, you will be having the electric field direction. So that's the one point to make a note. Now second, students, if you want to know the magnitude of an electric field, right, it will be equal to a magnitude, of the rate of change of, the potential, right, yes, per unit displacement, and that will be, students, it will be normal to the equipotential surface. Okay, so well, students, these are the points that you should be making a note. Along with this, students, the SI unit, of measuring the electric field from this relation, right, potential is measured in volts. Here, the displacement is measured in meter, so it will be a volt per meter. Now coming back, students, as I've told you that the integrations, the limits in the integration will taking care of this increment, right? Let me just show you how it is going to be. Well, this is the equation that we are having, right? If I take a line integral of electric field up, in a certain, the path, right? So students, let us consider we are going from, the B to a point A. Let us say we are moving this test charge from B to a point A. Now on the left hand side, it will be, students, integral of, the dV, the change in potential at, B to the potential at A, that will be limits. On the right hand side, it will be a minus integral of, again, students, it will be E dr. Okay, you guys know that, I've chosen the electric field to be along the x-axis and even the dr also along the x-axis, right? So that will be an integral of E dr. Limits will be from, R2 to R1. Right, the point B is at R2 and we are moving to the R1 distance, right? On the left hand side, students, you will see that it is going to be the potential at A minus potential at B, and on the right hand side it will be a minus, again, integral of that dr will be R, and again you substitute the limits, that will be giving me, students, R1 minus R2, right? Yeah. And what is that R1 minus R2? If you just see, that will give me some positive value. So the increment that is happening here in that dr, right, it's positive. We are moving from B to a point A, so the dr, is here is positive. The distance is getting increased, right? And that positive inside the bracket, when you, multiply with the negative, right, so you'll be getting some negative value, right? And if you just see, guys, what is this? Gives me the potential difference between a point A and a point B. Right, and what is that value I'm getting? Negative, right? So of course, guys, if we, that's the correct one, because if we just see, guys, the potential at B, is at it's a high, right? It's a high potential compared to at a A. So then when you take a VA minus VB, VB being a high, right? So the value I'll be getting a negative. Now let us go other way around. Okay, I'm moving this test charge from point A to the point B, right? This time, students, on the left hand side, the limits. I'll be putting, students, I'm going from, VA to the VB. On the right hand side, if you measure this distance R1 to R2, right, and again students, on the left hand side I can write it to be as a VB minus V, right? And on the right hand side minus E. After taking that integration, when you substitute the limits, it will be R2 minus R1, right? And what is this time we are having, right? We are taking R2 minus R1, so that will, R1 is greater than R2, so that will give me some negative value, right? And a negative and negative, students, that will give me a positive, right? So when you take a potential difference between a B and a A, that will give me a positive value, right? Yes. So if you just see that, students, when I took that R2 minus R1, right, that has given me a degree negative, dr, right? So that means there's a decrease in a distance happening here in this case, or the displacement is happening here in this direction, and the potential here is positive, right? Well, now students, if I consider this point A, let us say, to be at infinity, okay, my R1 goes to the infinity, right? And students, let me just see a point B is at some distance of R. Okay, now in that case, students, if you just see this integration, this is how I can write it. On the left hand side, integral, it is going to be a the potential at the infinity to the potential at B point into dV, right, is equal to, on the right hand side, minus integral of E dr, limits will be from infinity to R, right? And we know potential at infinity is 0, so which I can write as some V potential at particular point will be equal to minus integral of E dr, limits infinity to, it is going to be R, right? So students, if you just see this equation, right, the integration, by knowing the electric field at a particular point, right, by integrating it along that certain path, right, I can find out the electric potential at that particular point. So these are, students, something that you have to make a note. Now students, you must have seen another relation, something like this, right? Now how is that coming, right? If you just see, students, vector E is I can write it as when you deal in a Cartesian system, right, vector E can be written as Ex I cap plus Ey j cap plus Ez k cap, and same way vector Dr can be also written as Dx I cap plus Dy j cap plus Dz k cap. And students, when you take their dot products, right, we know that I cap dot I cap will give 1, right, I cap dot j cap will give 0, or even I cap dot k cap will give you the 0. So when you open up this brackets, right, what you will be having here, that minus, and inside the bracket, if you just see, it will be a Ex dx plus Ey, it will be a dy plus Ez dz, right? And students, suppose if you want to know the electric field on a particular along the x-axis, right, in that case I'll be taking a partial derivative. So if I want to know the Ex, it will be, students, minus dou V by dou x. Same with Ey will be minus dou V by dou y, and Ez will be a minus dou V by dou z, right? Now if you just see the, students, the electric field what we are having, right, again if I substitute those things here in the Ex, right, what I will be getting, students, it will be a minus dou V by dou x I cap plus minus it is going to be the dou V by the dou y in j cap minus dou V by dou z the along the k cap. And when I take that minus sign out, right, and just keeping that I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z, and again taking the potential out, so this is what I'll be getting. And inside the bracket, what you see, it's nothing but I can replace it by a del operator. Okay, so you can see here what I'm having, the electric field will be equal to negative of del potential, right? So this is what the relation we are having here. Now this is all the relations, students, that from this particular part where we have seen a relationships between the electric field and the potential. So these are so many relations which, students, you have to pick depending upon what kind of question has been asked. Okay, so please see that you're making all of them here, please see that you guys are making a note of it. So well, now since moving forward, we will be learning about the equipotential surfaces and their properties. Now here the word equipotential itself tells you that there must be some equal potential on the surface. Well, now here if you just see, this is my point charge, and we know that electric potential for a point charge is 1/4 pi epsilon naught, the charge q over the distance. And here if I keep that r fixed, the potential is going to be a constant. So if I choose my point here, keeping the r fixed, let us say some potential v, the same again here the point p, keeping the r fixed, right? So potential remains, you know, the same, right? So like that, in all possible direction, if you keep the distance fixed, the potential is going to be same. Now if you connect all these points, right, yes, you will be getting an surface which we will be calling as a equipotential surface. So you can imagine this, you know, in 3D, guys, to be has one spherical shell whose center lies, you know, at the center of the point charge. Well, now since I know as r increases, potential decreases, in that case, students, you can imagine, like, you know, there are n number of, you know, such spherical, concentric spherical, you know, shells whose center lies at the center of the point charge. Now it's again, students, very easy to understand, right? Now there are also a few properties that, you know, you have to make a note. Okay, the number one thing is that, students, let me just take this is my, you know, equipotential surface here, right? Now there's no work is done, okay, in moving the test charge over an equipotential surface. So let us say if you want to move a test charge from, you know, a point A to point B, right? So if you just see this relation, work done is nothing but charge into a potential difference. So we are talking about equipotential surface, so both the points A and B are at the same potential, so the difference comes out to be 0, so work done here is 0. So that's the number one thing. Second, students, the electric field, you know, is going to be always normal. The direction of the electric field will be always going to be a normal to the equipotential surface. Okay, if suppose you know, let us say if the electric field, you know, is along the surface, right, then again in that case, again, so the same explanation goes as well, right? Because if you want to move the test charge against, you know, this electric field which is along the equipotential surface, right, so in that case, the potentials, you know, over there, that if you choose the 2 points, the potential is going to be a 0 there, potential difference, right? So that will be again a work done is going to be a 0. So always see that the direction of the electric field should be normal, you know, to the equipotential surface. Now number 3, guys, if you just see this relation that we had, a relationship between the electric field and electric potential, right? Now if I consider that, you know, the potential, right, the, you know, the rate at which the change in potential, let us say, if it is changing by a constant or else by equal, you know, in an equal amount, let us say, right, in that case, students, if that dV is constant, right, you will see that, you know, here in this case, that E is inversely proportional to dr, or else dr is, you know, inversely proportional to E, right? So which tells me that, students, if suppose the electric field is strong, right, in that case the equipotential surfaces, you know, will be, students, you know, they will be closer. Okay, and if the electric field is weak, then in that case the, you know, the equipotential surfaces will be further apart. All right, so that's the number 3 point. Okay, then another last point, students, no two equipotential surfaces can intersect, you know, at a particular one point. Okay, because if that is the case, there will be a 2 values of an, you know, potentials, right, which are not going possible. So that's the 4th point. Now here, students, let us see, you know, some of the equipotential surfaces for, you know, a different charge system. So one we have already seen for a point charge, right? So the equipotential surfaces, students, will be, you know, concentric spherical shells whose center lies at the center of, you know, the point charge, right? And here in this case, since this is my positive charge, right, you will see that the electric field lines are coming radially outward, and the direction of the field lines will be perpendicular to the equipotential surface. Well, now since the next, let me just consider, you know, the 2 point charges which are, you know, let us say, you know, similar charges. Okay, so let us say a positive charge and positive charge, right? Now here, if you just see, students, the equipotential surfaces, you know, if you just see here, you know, the region which is between these 2, you know, similar charge, two like, you know, the charges, right? Here in this case, you will see that equipotential surfaces are further apart, right, which tells me that there must be some weak electric field in this region. Now if I take, you know, students, the 2 point charges separated by some distance, and which are you know, both are, you know, the opposite charges. Okay, let us say positive and negative charge here, right? So here in this case, you will see that equipotential surfaces are closer, which is an indication of the, you know, the electric field here is strong. Now when you're having, students, the uniform electric fields, right, you will see that the line of force, or else the field lines, you know, these are parallel straight lines, and here the equipotential surfaces, you know, you will see that they are going to be plane, okay, right, which are going to be perpendicular to the the electric field lines, and they will be at an equal distance, right? So this is how the equipotential surfaces will look like for for the the uniform the electric field. Now, like the electric field lines, there's equipotential surfaces also gives us the visuals from where we can get the magnitude as well as the direction of an electric field in the electrostatic space. Now, since this is all about the equipotential surfaces and their properties. Now, this time we will be using this relation in getting the electric potential of a solid conducting sphere. Now, when I say a conductor, students, we know that the charges will be residing only on its surface, right? Now, here, by taking the line integral of an electric field along a certain path, I can easily get my electric potential. Now, if you remember, students, in the first chapter, we have already done the calculations of an electric field for a same solid conducting sphere. And these are the three different cases which we had taken, right? When the point P lies outside the solid conducting sphere, we are getting the electric field to be as 1 upon 4 pi epsilon naught a charge q over the square of the distance, right? And when the point P lies on the surface of it, right, we know the electric field here in this case 1 upon 4 pi epsilon naught the charge q over the square of the distance, and here in this case distance is nothing but the radius of the solid conducting sphere. And the electric field inside this conducting sphere was 0, since if you just take a Gaussian surface inside this conducting sphere, the charge enclosed by the Gaussian surface comes out to be 0, so electric field was 0. Now, since we will be using this relations, okay, in this relationship that we're having between the potential and electric field, okay, and since this is how the graphs looks like for an electric field, okay, so please make a note of it. Now, here, students, once again we are doing the same three cases, right? So let us start. Let's consider a point P to be at some distance of r from the center of the solid conducting sphere. And students, if you just see what we know here, we know the electric field, what is at this particular point P, right? We already know that, right? So we will be taking that integration of this relation. So on the left hand side it will become integral of dv. It will be from the potential at infinity. I'll consider infinity as my reference point to a potential at this point P, and the students, it will be equal to minus integral of the electric field. I know it is q upon 4 pi epsilon naught r square into dr, and limits will be going from infinity to the point r, right? Well, now since on the left hand side if you just see the potential at point P minus potential at infinity will be equal to minus, I can take that q upon 4 pi epsilon naught common out, constant out, okay, and it will be an integral of it is going to be 1 upon r square dr, limits infinity to r. Now I know that, students, the potential at infinity is going to be a 0, right? So on the left hand side I can write it as the potential at point P. So instead of writing that potential at point P, I'll just write it as a potential at point P at the outs, okay, outside the the sphere, okay. Just let me write it as a v out, okay, just to know that we are finding the potentials outside the conducting sphere. And on the right hand side, students, we know that minus q upon 4 pi epsilon naught, and when I take an integration of that 1 over r square, I know that, students, it will become when I take that r square going up in the numerator, right, it will become r to the power minus 2, and when I take an integration of that, it will become r to the power minus 2 plus 1 divided by minus 2 plus 1, right? And if you just see, guys, what we are having, r to the power minus 1 divided by minus 1, and which I can write it to be as a minus 1 upon the r, right? And the limits will be from infinity to r. Now on the second step, guys, I can just substitute the limits here back. So what I'll be getting, minus q upon 4 pi epsilon naught, and when I substitute over there, it will become minus 1 upon r minus 1 upon infinity, right? And students, the second term goes, it becomes very negligible, right? It will be almost 0, and when you multiply that, you will be getting positive q upon 4 pi epsilon naught r, right? So you can clearly see that electric potential, what we are having here at this point, is 1 upon 4 pi epsilon naught the charge q over the distance, that's r. Now when I consider a point P on the surface of this conducting sphere, I know that, students, here in this case distance is nothing but a radius of the solid conducting sphere. So this is how the equation will look like on the surface, the electric potential on the surface. And since we know that electric field inside the conducting sphere is 0, So if you just take this relation, you can clearly say that, you know, electric field is nothing but a negative of a potential gradient, right? If the electric field is 0, that means the potential has to be a constant, right? So whatever potential we are having here on the surface of this solid conducting sphere, the same potential will be throughout the, you know, entire inside this, you know, the conducting sphere. So this is what, you know, we are having here. Now students, instead of this solid conducting sphere, let us say if you're having, you know, conducting, you know, spherical shell, right? Now here in this case, students, previously we have discussed about a solid sphere, right? So this time it's a shell. Okay, now I know that, students, again the charges will be residing only on its surface. So even if you take a point P over here, the potential remains same what we have got for a solid conducting sphere. Even if I choose my point P on a, you know, surface of the shell, the things remains the same. The same equation goes as well here as well. And we know that inside this, you know, the shell, the electric field is 0, right? Yes or no? If you just take a Gaussian surface, we know that no charge is enclosed, so it's 0. So if the electric field is 0, whatever, you know, potential we're having on the surface of the shell, the same goes, you know, inside as well, right? So these are the, you know, the equations which we had obtained for a conducting, you know, solid sphere. The same, you know, we can use it for a spherical shell. Now students, moving ahead, we will be going with the next is we will be trying to find an electric potential of a non-conducting, you know, solid sphere. Let us see that. Now students, this is a non-conducting solid sphere that we are having here, right? And students, when we're talking about a non-conductors, we know that whatever charge you put it on this non-conductors, they will be just residing in that particular region. It won't be moving from one region to another region like how we have seen in the case of conductors, right? The charges were just, you know, getting distributed across, you know, the entire on the entire surface, right? But here in this case that is not happening, right? It will be just at the same place where you put them up on this non-conductors. Now here in this particular scenario, we are considering of a non-conducting solid sphere to be uniformly charged sphere. Okay, that is, the charges will be, you know, entire, you know, throughout its volume. Okay, this is how the charges will be. It will be uniformly charged sphere. And the students, with the help of this relation, again we're going to find the electric potential at 3 different cases when a point P is outside this non-conducting sphere, on the surface, as well as inside. Now here we need the electric field, right? Because what we'll be doing, we'll be taking the line integral of an electric field along a certain path, right? So we need electric field, and from the first chapter, students, we have already obtained the electric field for a non-conducting solid sphere. And these are the equations, right? If you just see, when the point P is lying outside this non-conducting sphere, it's 1/4 pi epsilon naught, the charge q, over the square of the distance. And on the surface, we know that the point P, the distance is nothing but the radius of it, so it will be, students, just replacing by r, right? Capital R. So this is the 2 equations that we're having. Now the third scenario, third case, right? This time the electric field won't be a 0 inside this non-conducting sphere, right? Because you can see that a charge is inside it, right? And what is the equation? How the equations look like? It is 1/4 pi epsilon naught, the charge q, into the r, right? That's the point, that's the distance, you know, of the point P from the center of it, right? Over the r cube, right? So this is what the equation that we have it. Now students, we will be making a use of this, you know, the equations in getting the electric potential. And students, you know, before that, guys, this is the graphs of an electric field, how it varies with the r. Okay, so well, now students, let us begin with the, you know, the calculation part. If you just see, students, I'll be just considering my point P somewhere here at a distance of r from the center of it. So once again, students, the same steps goes here as well. What we have done for the, you know, the conducting sphere, right? The same steps, it goes here as well, right? Because the electric field is, you know, the equation, if you just see, it's the same, right? So you know, these are the steps you can see here. Once again, you take the integration of that, and when you take the integration, you will be ending up, you know, the electric potential to be as 1/4 pi epsilon naught, the charge q, over the distance. Okay, it's the same integrations, so you can just have a look at it, right? Now students, when the point P is on the surface, right, so you have to just replace that small r by a capital R, and this is the second you know, the case that we're having here. Now what about the third case, right? So that for this we have to do an integration, right? So students, we'll just see this. This is what we are having here, right? I'll be just considering my point P to be inside this, you know, solid non-conducting sphere, right? at a distance of r from the center. So this is the point, and capital R is the radius over here, right? Here I'll be moving my test charge from the surface to the point P, which is inside the non-conducting sphere. Now see students, if you want, you can also take the infinity as a reference point. Okay, in that case only the limits in the integration will be changing. So in my case, I'll just take that test charge on the surface, and I'm moving it from surface to the point P. So students, over here it will be integral of dV, potential at the surface to the potential inside this the non-conducting sphere will be equal to minus integral of, I know what is the electric field inside this sphere, which is Q upon 4 pi epsilon naught, the R upon the R cube dr. Limits will be capital R to a small r. Now on the left hand side, since I know electric potential inside minus electric potential on the surface will be equal to minus over there, since whatever the constant is there, I can take out the integration. It will be a Q upon 4 pi epsilon naught, the R cube integral, it is going to be R dr. Limits capital R to small r. So what is the integration of R? Integration of R is R to the power, you can see it is going to be a 1 plus 1 over, it is going to be a 1 plus 1. So it is R square upon 2. And again, the limits will be from capital R to a small r, right? And when I substitute the limits there, I'll be getting, students, inside the bracket, if you just substitute, it will be R square upon 2 minus capital R square upon 2, right? So now, students, you can just open it up. When I open it up, right, the first term that I'll be getting here is minus Q upon 4 pi epsilon naught R cube. It is going to be a R square upon 2. Again, second term, minus into minus positive, Q upon 4 pi epsilon naught R cube, and it will be a capital R square upon the 2. So this is what I'm having. Now students, whatever things are getting cancelled out, I'll be just cancelling them out. I can see from a second term, R square will be getting cancelled with R cube. So only one R is there in the denominator. So now just, I just rearrange it. So this is how the equation, will look like, right? Now here, if you just see, students, right, on the left hand side, what I'm having the electric potential inside minus electric potential on the surface, right? So we are interested in electric potential inside the sphere. So I can take that V, electric potential on the surface on the right hand side. When I take it on the right hand side, I know what is the electric potential on the surface. It is 1 upon 4 pi epsilon naught, the charge Q over the radius of that non-conducting sphere. And if you just see, students, when I add this first and second term, I can add it up, right? So when I add it up, it will become 3 by 2, 1 upon 4 pi epsilon naught, the charge Q over the, it is going to be a R, right? That is what I'm having. And again, that, the term minus Q upon 4 pi epsilon naught, right? It is going to be, the R square. Yeah, it is going to be Q upon 4 pi epsilon naught R cube, R square by 2. That is what I'm having here. Now here, if you just see, students, I can just take out the common out, here I will be getting, students, Q upon 4 pi epsilon naught, that is going to be R. That's the constant common here in this case of both the terms. So inside a bracket, I can put 3 by 2 minus half R square upon capital R square, right? So this is the equation that we are having here, which you have to make a note. Now students, if I consider a case where the point P is just lying at the center of this non-conducting solid sphere, in that case the small r comes out to be 0, right? And what will be the, students, the electric potential inside at the center of this is going to be, students, if you just see that Q upon 4 pi epsilon naught times capital R, right, is nothing but the potential on the surface, right, will be a 3 by 2 times, right? 3 by 2 times the potential on the surface. So this is the a special case that we have discussed. Now students, these are the equations which are important from the competitive exam for a non-conducting solid sphere, right? And this is how the potential graph will look like as you vary the R for this non-conducting solid sphere. Now students, when you talk about non-conducting hollow sphere, this is my solid sphere, non-conducting solid sphere, right? So for a hollow sphere, guys, the charge is again on the surfaces, right? So if I choose a point P here, the same equation we will be getting. And what about on the surface? Again, the same relation what we have got it here, right? Now we know that the electric field inside this hollow non-conducting sphere is 0, right? So over there, students, whatever potential you are having here on the surface of this hollow sphere, right, the same will be inside it. So that's the one change that you should be making a note. Now, since these are altogether the equations which you should be making a note for a hollow sphere as well. Now, moving forward, we will be going with the problem solving part. So let us quickly see that. Now, if you just see this question, it says a test charge Q is moved without acceleration from A to C along the path A to B and then from B to C in an electric field E, as you can see here in this figure. The first part says calculate the potential difference between A and C, and the second part, at which point of the two is the electric potential more and why. Now, students, when you see a potential difference, right, we know that, students, it doesn't depend upon the path along which the test charge has been moved, right? So here we are interested only in the initial position of the test charge and the final position, right? Though here in this question it has been told that the test charge has been moved from A to B and then from B to C, right? For us, we know that we are talking about conservative forces. So students, only here we interested in the initial and the final position. Now, students, here we are moving the test charge from A to C. So we are interested in the potential difference, between a C and A, right? The potential at C minus potential at A. This is what we are interested in. So I know that, students, electric field E is nothing but negative of the potential gradient that will be giving dV by dr, right? And I know, students, here in this case it will be a minus potential at C minus potential at A over the change in distance. So this is happening if you just see from, we are moving it from A to C. So it is going to be a 2 minus 6, right? And I can get it at minus VC minus VA over 2 minus 6. That will give me a minus 4. Minus minus gets cancelled. That will become positive. And here I'll be getting electric field to be as VC minus VA by 4. I can just rearrange it once again. The potential at C minus potential at A will be a 4 times A. So this is what I'm having my answer for the first part. Now, second part, students, at which point of the two is the electric potential more and why. Now, students, if you just see the direction of the the electric field, right, we know that it will be always towards the decreasing potential, right? So that means that the point C will be at a higher potential than at the point A, right? So VC is going to be greater than the potential at A, because the direction of the electric field goes from higher potential towards the lower potential region. So this is my answer for the second part. Now here, if you just see this question, the two identical plane metallic surfaces A and B are kept parallel to each other in an air separated by a distance of 1 centimeter, as you can see here in this figure. Surface A is given a positive potential of 10 volt and the outer surface B is earthen, that is grounded. And the first part says what is the magnitude and direction of the uniform electric field between a point Y and Z. And second part, what is the work done in moving the charge of 20 microcoulomb from X to a point Y. Now, since we are having these two metallic plates, right? And on a plate A, or else on a surface A, we are having the positive potential of 10 volt. Let us say here we are having a 10 volt potential on the surface A, and the surface B is earthen, or else it's grounded, right? So I can consider this to be at a 0 potential, right? Yeah. And if you just see, students, what is the magnitude and direction of the uniform electric field that has been asked. To solve this question, guys, again I'll be using the same relation that I'm having here. Electric field is nothing but negative of the potential gradient dV by dr. So what is the change in potential here? If you just see, this is my, on a surface A, it's a 10 volt, surface B, it's a 0, right? So the change in potential here in this case, between these two, surfaces, if I consider it, so it is going to be minus, it will be the change, it is a 10 volt. And what is the distance, guys? Distance of separation between these two surfaces is 1 centimeter. So this I have to convert it into meter. I just divide this 1 centimeter by 100, or else it will become 10 to the power minus 2. I take it here as a minus 10 to the power minus 2, right? And I can just say that, this goes up, it will be a minus, 1000 volt per meter, right? So this 10 to the power minus 2 goes up, becomes positive, right? And that will give me a 1000 volts per meter. So that's the magnitude of the uniform electric field between the points X and Y. Okay, since we are talking about this X and Y, so the electric field here at this points will be the same. Now, students, we have to find out the magnitude and as well as the direction of the uniform electric field between the point Y and Z, right? Now, what will be the direction of an electric field between the point Y and a Z? Now, if you just see, students, the surface A is at a high potential, surface B is at a lower potential, and we know, students, that the direction of the electric field will be always going from a higher potential region to a lower potential region, right? So this is going to be, students, the direction of the electric field lines going from Y towards the Z. Yeah, it will be always in a direction in which you are having a decreasing potential. Now, students, the second part of this question, what is the work done in moving the charge of 20 microcoulomb from a point X to the point Y? Now, if you just see, students, both the points X and Y are on the surface A, right? That means we are talking about both these two points are having an equal potential. The potential at point X is of 10 volt. Potential at Y is also of 10 volt, right? And if you just remember, guys, what is a work done relation? Work done is nothing but, the change in potential difference. Let us say potential difference, between Y minus potential at X into the charge Q, right? So if you're having the same potential at both the points, right? So work done is going to be 0 here in this case. So that's the answer for my question. Now, students, the potential at point X measured in micrometer due to some charges situated on the x-axis is given by V of X is equal to 20 by X square minus 4 volts. The electric field E at X is equal to 4 micrometer is given by dash, right? And these are the 4 options that you can see on your screen. Now, since again, it's very simple. We know the relationship between the electric field and the electric potential. So that will help us here. Now, first of all, students, let me write this potential to be something like this, right? What I have done here, I've just taken the denominator into the numerator, and this is how it looks, right? Now, here, this is the relation that I'm having here. So all that I have to take is a derivative, right? And the students, later at X is equal to 4 micrometer, by substituting that value, I'll be getting my answer. So if you just see, students, here, let us start doing this. We know that electric field E here is going to be a negative of d by dx. What is the potential? Let me write it here, that V 20 x square minus 4 to the inverse, right? And let's close the bracket. So here I know that, students, 20 is constant. So let me take it minus 20 here. And when I'll be taking the derivative of that x square minus 4 to the power minus 1, that will give me, students, minus 1 bracket x square minus 4. And in a power here, it will be minus 1, minus 1, right? So that will give me minus 2 into the derivative of this x square. That will give me a 2x. So this is what I'm having here. So I can just multiply this 2 and 20. That will give me a 40. So minus and minus positive. So that will be a positive 40x. And this, I can take this x square minus 4 to the power minus 2 in a denominator. So that will become x square minus 4 the whole square, right? So this is what I'm having here. Now, so students, from here, I have to just make a substitution of this X is equal to 4 micrometer here in this, and I'll be getting electric field E to be as 40 into what is X? It's a 4 micrometer. So let me just, keep that micrometer as it is. Okay, I'll just take a 4 here. It's in a micrometer. Divided by, students, it is going to be a 4 square minus 4 the whole square. So 44s, I know it is 160. 4 square will give me a 16 minus 4 the whole square. And I know 160. 16 minus 4, that will give me a 12. And 12 square, that will give me a 144. So from here on, students, I just cancel out here. 2 80s are 160. And I can say that here in this case, 2 72s are 144. And 8 10s are 80. And 8 9s are 72. So that will give me, students, 10 by 9 volt per micrometer. So that will be an electric field, and that is going to be in a positive, x axis, right? In a positive direction. So this is the answer, guys. I can say 10 by volt in micrometer and in a positive x direction. That's the correct answer for this question. Now here, if you just see, students, the electric field in a region is given by vector E is equal to AX plus BI cap, where E is in Newton per coulomb and X is in meter. The values of constants are A is equal to 20 SI units and B is equal to 10 SI unit if the potential at X is equal to 1 is V1 and that at X is equal to minus 5 is V2, then V1 minus V2 is dash. Now, students, to solve this particular question, right, we're going to use the same relation that we had. dV is equal to minus E dr. And this time, students, what I have to do is that I'll be taking an integration. So integral of dV, students, limits, if you just see, we are interested in a potential, between a point 1 and a 2. So the limits will be going from V1 to V2 to V1 is going to be equal to minus integral of what is an electric field. It's AX plus B along the I cap. So here, let me just write it here, AX plus B. That's happening along the I cap, right? So here, X is in meter, right? And that small, increment, that small change we are making here is along the x-axis. So this is the dx. And if you just see, students, what will be the limits for here in this case, right? So what has been told, at x is equal to 1, the potential is V1, and at x is equal to minus 5, the potential is V2. So my limits, students, for this, the V2 is when x is equal to minus 5 and it will be going to 1. So these are my limits for this on the right hand side. Now from here on, students, it's very simple. You have to take just an integration V1 minus V2. So here on the right hand side, that AX, right, minus A is constant, integration of X, I know it is X square by 2. Limits will be going from minus 5 to 1, right? And again, that minus into B, right? B is a constant and integration of 1, I know it is going to be X. Limits will be from minus 5 to 1. So now just substitute the limits here in this case. So V1 minus V2 minus A, and when I substitute the limits here, X square, right? So upper limit is going to be a 1 square upon 2 minus the lower limit. You just substitute at the place of X, you have to substitute minus 5 the whole square divided by 2, and this is what I have made a substitution here. And a minus B is going to be 1 minus of minus 5, right? So this is what I'm done. Now just open it up. Let us see here, guys. It is going to be V1, right? Let me just do that here in this case. So here, if you just see V1 here in this case, V1 minus V2, I'll be getting, guys, V1 minus V2. It will be equal to minus A, and inside the bracket, what I'll be having, it is going to be a 1 by 2. And if you just see minus 5 the whole square, that will give me a positive 25. And I can say that it will going to be a 1 minus, it will be a minus 25 by 2. That is what I'm having here. Minus B, and here it is going to be 1 minus into minus positive. So that will become positive 5. So now you can substitute the values of A that you're having here. It's 20 SI units and B is of 10 SI units. So let me just substitute that. A here is minus 20. And inside the bracket, I'll be having 1 minus 25. That will give me a minus 24. And this is by 2. Minus B, here is, B is 10. And it is going to be a 6. So from here on, I can just, solve this. So this is going to be a 2 1s are, 2 10s are, 10 24s are. It's going to be a 240 and it will be a positive. Minus into minus positive. 10 6 are 60. So that is going to be a minus 60. So what I'll be having here, potential difference is of 180 volts. So that is going to be a V1 minus V2. So what we have been asked. So that's the answer for this question. Now, if you just see this question, if potential in a region is expressed as V as a function of x, y, z to be equal to 6xy minus y plus 2yz, the electric field at point 1, 1, 0 is dash, right? Now, to solve this particular question, since we need this relation here, right? So what I'll be doing here is that I'll be taking a partial derivative of this potential that is given to us, right? So let me just solve this separately so that it becomes easy for you guys to understand, right? So what I'll be doing is that I'll be taking a partial derivative of this potential, okay, along the x, let us say. So let me just do that. Dou of v by dou of x. When I do that, it will be a dou by dou x. What is the potential that I'm having here? Let me just put it in a bracket. It will be a 6xy minus y plus 2y z. Okay, so let me just use the symbol as a z is something like this, so that you're not getting confused here. Okay, and students, when I'll be taking a derivative of this, okay, I can say that it will be equal to, guys, I can very well say that it's going to be derivative of x here in this case will be, guys, it will be x to the power 1 minus 1, so the power comes to 0, right? So let me just do that. It will be a 6, and it is going to be here x to the power 1 minus 1, that will be 0 y, and here this goes to 0, plus even this term goes to 0. So what I'm having here is just 6y. So that's the answer for this. Same way, students, let me also do it for the others as well, right? So when I take the partial derivative, and I take the partial derivative of, let us say, along the y, so that will be dou by dou y. So again 6xy minus y plus 2y z, right? So here in this case, again, if you just see, it is going to be this time as well 6x I'll be getting, right? Because that derivative of y is going to be y to the power 0, and which will be a 1. And here again, this is going to be also 1, guys, minus 1. And here in this case, it will be a 2 times the z. So this is what I'm having. Same way, let us also do it for the last that we are having here. That is, when I take a derivative, let me just do it here, dou of v by dou of z, that will be dou by dou z. Potential will be 6xy minus y plus 2y z, and here in this case the first term goes to 0, right? Even second term goes to 0, so only we are having the last here, so the derivative of that will be 2y. So this is what we are having here. Now I'll be just making a substitution of this in this, what I'm having. Electric field, students, I know electric field is nothing but minus dou v by dou x, which I have already done. So that is 6y, so it will be a minus 6y. Okay, and I can say that, students, here in this case it will be 6y, yeah, and let me write it here as a I cap minus it is going to be this is going to be a 6x minus 1 plus 2z j cap, and minus it is going to be 2y k cap, right? So this is what I'm having here. Now students, we know the points 1 comma 1 comma 0, right? These are nothing but x comma y comma z. So just I have to substitute them up here. So the electric field here, and I substitute here y is 1, so that will give me a, students, minus 6 I cap, and here as well when I substitute for x is equal to 1, so that will become minus 6, yeah, and here this is also minus 1 here in this case, yeah, and plus 2 times the z. Z is also 0 here, so that terms goes there, right? It becomes 0. So let me erase here, so that will go 0, and I can say that this is going to be my the j cap. This is going to be my j cap minus 2 k cap, right? So when you open it up, students, I can say that electric field E will be equal to minus 6 I cap, and here again minus 5 j cap and minus 2 k cap, right? So if I want, I can also write this electric field to be as minus bracket 6 I cap plus 5 j cap plus 2 k cap, and this is what the answer I'm having for this question. If you just go and check it out, the correct answer that you see here, it's the option C. That's the correct answer for this. Now here in this today's session, we started with the relationship between the electric field and the electric potential. So students, these are the equations, you have to make a note. So here, if you just see, students, electric field is nothing but a negative of a potential gradient, and the same relation, students, when you take a line integral of an electric field, you can also find out potential at a particular point in an electrostatic space. And we have also used this the equations in this today's session while solving some numericals as well, right? Then students, we also discussed about an equipotential surfaces. So the 4 properties that we have discussed here, we have also seen an equipotential surfaces for a different charge system as well, right? And finally, we also used this relation between the potential and the electric field in getting the electric potential of a conducting solid sphere, right? And then as well as for students non-conducting solid sphere, right? So this is what the equations you have to make a note. And since this is all for this today's session, okay, see you guys in the next session. Till then, bye bye, take care, keep learning.